I'd like to introduce Tom Stuart. Tom is from London. He's been doing Ruby for 9 years. And he's a former Bay Area resident. He lived here in '99. Then he moved to London, and this is now his triumphant return. Tom is the recent author of Understanding Computation. He came on the Ruby Rogues as a guest to discuss his book, episode 120. Blew all of our minds, and yet here he is anyway. So big hand for Tom and Impossible Programs.
Cool, thanks Josh. Hi everyone, thanks very much for coming to this talk. Yeah, I'm going to talk to you about some impossible programs. So how can a program be impossible? Like, what does it mean for a program to be impossible? And I'm going to try and explain that to you by reminding you of two facts of life. The first fact of life is that we kind of collectively demand universal systems. Now, what do I mean by a universal system? Well, I'm sure it's obvious to you that you could take, for example, any Python program and translate it into Ruby, right? You could just go through the program. For every piece of Python syntax, you just replace it with a bit of Ruby syntax, and by the time you're done with that, you now have a Ruby program that does the same thing as the Python program you started with. And the fact that you're able to do that doesn't mean that Ruby is some super awesome programming language, although obviously it is. It's just like the sense in that these two programming languages are they have the same kind of power, and you can do it the other way around as well. So there's nothing special about Ruby. You can do the same thing with Python. You can just take a Ruby program and translate it into Python. And actually, there's something a bit deeper than that. It's not just the case that for any individual program that's written in Ruby or Python, you could convert it into the other language. It's also possible for you to write a single Ruby program, which is as good as all Python programs. And what I mean by that is you could write a Python interpreter in Ruby. That's one Ruby program that you write, and then you're done writing it, and then you can feed it some data, which could be a Python program, and it will just be able to do something different depending on the data that you fed into it without you having to go and change the Ruby code that you write. And again, there's nothing special about Ruby here. You could do it the other way around. And there's nothing special about the combination of Ruby and Python here. You could just as well say, I'm going to implement a JavaScript interpreter in Ruby, or I'm going to implement a Ruby interpreter in JavaScript. So there are a whole bunch of these systems, and they have this special relationship with each other, which is that for any individual program or design that is expressed in one system, you can convert it into any of the other systems. And more particularly, you can kind of write a simulator for any of these systems in any of the other ones. And there's actually like a whole constellation of these systems, a whole bunch of things that we call universal systems. Anything that you... Any of these can simulate any other of these, right? And this okay. don't do CSS heckles. So I'm calling this, I'm calling these universal systems. Some people call this property Turing completeness, right? It's basically the same thing. So why are we so interested in universal systems? Well, the essential property of universal systems is that they can run software, right? They are able to, you can create one once, and software means that you can kind of feed some data into a system, and it can behave differently depending on what that data looks like, right? Ultimately, we don't just want automated machines that can do work for us. We want some general purpose machines that we can build or design once, and then having built and designed them, we can then feed them data and have them do any job just based on what data we've put into them. And MRI is one of these general purpose machines, right? MRI is a C program that you can download onto your computer and install, and then even though it's only, one program, that doesn't mean it can only do one thing. It can actually do a wide range of things depending on what data you put into it. So that's the first fact of life. Like, we want these universal systems so that we can have general purpose machines. The second fact of life is that programs are data. And that's kind of obvious. What I mean by that is, if you go into IRB and you type in a little program, and you execute it, and it does what you expect it to do. Now, you can think about that as a program, as like a series of instructions that you're giving to the computer, but you can also think about it slightly differently. You can just think about it as a string. And Ruby knows about strings, so I could take that program and put it inside a string, and now I've got a program which is inside another program as data. And that's kind of a mundane observation, but the consequences of this are quite profound. I mean, this means that like any program can be expressed as a string, and strings are just sequences of bytes. So I could just take that string and break it down into a sequence of bytes, right? That's still my original program, but I'm just kind of exploded it out into its component pieces. This is essentially just a giant binary number. I could just turn that giant binary number into a giant decimal number. So, in some sense, the kind of hello world program in Ruby is like Ruby program number 979654 and so on, right? And that's not a reduction, that's not a reduction of the original program. That is the original program. I'm just showing it to you slightly differently. And if I gave you that number, then you could type that number in, and then you could break it apart into its component bytes, and you could turn those bytes into characters and concatenate them together, and then you could evaluate that string. And I have given you that program by giving you the number. So these are the two facts of life, right? We want these universal systems so that we can have general purpose machines whose behavior we can control just by feeding them data. And we have a special kind of data that we call programs, and those are the kinds of data that we want to feed into these universal systems. Now, the combination of those two facts of life has got this sort of inescapable consequence, which is that some of these programs that we write for these universal systems are inevitably going to contain infinite loops. And it's not necessarily obvious what the connection is there, so let me just walk you through it. So what universality means, essentially, every universal system can simulate every other universal system, and that includes itself. And more specifically, that means that every universal programming language can implement its own interpreter. So if all we know about Ruby is that it's a universal system, then that means we must be able to write some kind of method like this in Ruby that can evaluate a Ruby program, so like a Ruby interpreter in Ruby. And I haven't actually filled in the details here. That's just kind of like an exercise for you, but I just had to fit it all on one slide, right? But the way this would work is that you would read in a string, you'd take a program, which is just a string, and you would parse that program into some intermediate representation, like an abstract syntax tree or whatever, and then you'd evaluate that program on some string of input, so assuming that's what's going to be provided to this program on standard input. You kind of walk over the abstract syntax tree, you find all the instructions, you do whatever those instructions say to do, you figure out what the output of that program is going to be, and then you return it. And in particular, this is quite easy to write in Ruby because Ruby has got an eval method in the kernel module, right? But even if Ruby didn't have eval, you could still write this. And I recommend you come to Ryan's talk this afternoon if you want to find out how we can actually do this kind of thing in Ruby. So this is simple. If I've got this evaluate method in Ruby, then that means I can do stuff like this. I can say, evaluate this program that reads in a string from standard input and reverses it, and here's the string I want you to read in from standard input, and what's the output? Well, it's just that string reversed, right? So the evaluate method is asking a question, really, and the question is, if I evaluated this program, then what would its output be? Now, if it's possible to write this evaluate method in Ruby, which it is, then it's possible to also write a method called evaluate on itself, and there's nothing special about this. This is just a method that takes one argument instead of two, and it provides that argument twice to evaluate. And so essentially what that's going to do is evaluate the program, but it's going to provide the source code of the program as its input. So what this means is that if I called this evaluate on itself, I just give it a program, and then the output of that is just going to be that program reversed, because that is what this program does. So if you can write evaluate and you can write evaluate on itself, then you can write this longer program, which is define evaluate on itself, and then read in a program from standard input, and then evaluate that program on itself and see what its output would be. And if the output of that program would be no, then output the string yes, and otherwise output no. So this is a little bit contrived, but the program I've written here is one that I'm going to call doesitsayno.rb, right? This is something which will read in a program, evaluate it against its own source code, and then tell you whether the output of that program is the literal string no. And this is all totally sensible, right? I can stick a program into this. If I echo that print standard in read reverse into it, into Ruby doesitsayno, it will evaluate that program on itself and see what the resulting string is. Is the resulting string the literal string no? Well, no, it's not going to be. It's going to be like the reverse of that string, so the answer is no. Whereas if I echo a different program into it, this program that prints no if the literal text that it reads in contains the string no, then that is going to output the string no, so the answer is yes, right? That program does say no. So this is all, there's no problem with any of this, but the difficult thing is what happens if you feed this program into itself? Like, what is the outcome of that process going to be? Let's think about it. So I've got my doesitsayno.rb. I can sort of effectively take a copy of that program and feed it into itself. Now, there are two obvious things that might happen, right? It might output yes, or it might output no. Now, are either of those like the correct answer? So the question that this program is supposed to be answering is what happens to this program? What does this program, when you feed this program into itself, does it say no or not? And so if it says yes, then the answer to the question of when you feed this program into itself, does it say no, is no. So it shouldn't have said yes. That's the wrong answer to the question. But the same thing applies the other way around. If this outputs no when I feed it into itself, then the answer to the question, does it say no, is yes. So no is not an acceptable output either. So assuming that this program works properly and does what it's supposed to do, neither of those is the output that we want. So what other options are there? Well, it could maybe just output some other string. It could output maybe, or it could output the empty string. But then when you go look at the source of the program that we've written, you can see that it's not able to do that, right? There are only 2 strings that it could possibly output. So that's not the right answer either. So given that this is all code that we could really write, there's only one possible extra outcome, which is that this program just never finishes. It could just sit in a loop forever, kind of running and running and running and never giving you an answer. And in fact, if you write that program, that's what actually happens, assuming you've got enough stack space, right? So the argument goes like this. Ruby is a universal system. And that means that we can write this evaluate method in it. You can write an interpreter for Ruby in Ruby. And then if you can write evaluate, that means you can construct a special program that loops forever. Now, I know that Ruby has got syntax for writing infinite loops. You can just write while true, do end. But you don't actually need to know that. You just need to know that Ruby is a universal language. And so without knowing anything about what syntax there is, there must be some way to create one of these special programs that loops forever. And this actually suggests one impossible program, which I'll show you now. So sometimes these infinite loops in our programs are bad, right? They represent a bug. If you have an infinite loop in your Rails controller action, then that means you've got a problem. So if we found that we were sick of having these infinite loops showing up in our programs, we could take features out of Ruby until there was no way to cause an infinite loop in a Ruby program. And that's totally doable. It's just an engineering problem. We could take stuff out. We could say, we're not going to allow unlimited iteration. We're going to take out while and until and loop. We're only going to let you iterate over finite data structures, so you can send each message to an array, for example. We'd have to take out procs, because you can write procs like this that loop forever. And that's actually a special case of a more general problem, which is recursive method calls. That loops forever because it's recursively calling the call method. We don't want people to be able to write a foo method that can call foo, because then you've got an infinite loop. So we'd have to come up with some kind of syntactic constraint. For example, we could say that a method can only call other methods that come after it in the alphabet. We don't want any blocking I/O, because then your program would be able to sit there blocking on input forever and never finish, and so on, like a million other things that I don't want to talk about. But this is something you could work through and do. And if we did this, we'd end up with a new language that was Ruby with a whole load of stuff taken out. We could call it Rub. This is like, because it's like Ruby without the Y Combinator, right? Oh, man. This is a tough crowd. Come on, San Francisco. So there's an impossible program here, and the impossible program is it must be impossible to write an interpreter for this language in itself. You can't write a Rub interpreter in Rub. And why is that? I've already told you why it is. If you could write like the Rub version of evaluate in Rub, then you could use that evaluate method to construct a special program that looped forever. But sort of by construction, this language doesn't let you write programs that loop forever, so it must be impossible to write that in it. And that's kind of weird, because the whole point of this language is that when you evaluate it, it definitely finishes. So a Rub interpreter is a program that always finishes. A Rub interpreter can't have an infinite loop in it. So that feels like exactly the kind of program we should be able to write in this language, but we can't for the reason I've just showed you. This Rub language can express some programs that always finish, but not all programs that always finish. Now, you could write a Rub interpreter in some other language, of course. You could write one in Ruby. And you could actually write one in another one of these languages that is crippled so that it can't have infinite loops in, a sort of a more powerful language. So you could sort of step up into a more powerful system and write an interpreter, but you can't write the interpreter in the language itself. So that's all kind of, like, to be generous, that's mildly interesting, right? But what about Ruby? I've showed you a toy language and showed you an impossible program in it, but what about a language we actually care about? So that evaluate method is an impossible program for Rub, which means that Rub isn't a universal language. But universal systems like Ruby have these impossible programs as well. And let's look at some examples and think about this. So here's a Ruby program. This just reads in a string from standard input and then prints out that string upcased. And just by looking at that program, we can tell that that Ruby program is always going to finish. And the asterisk there is like assuming that standard input is finite and non-blocking, right? I'm not interested in the operating system. I'm just interested in what this program does when it's read a string of input. So that program always finishes. If I modify it and put an infinite loop in the middle of it, then this is a program which obviously always loops forever. So these are two specific examples of Ruby program that exhibit certain behaviors, and by behavior I mean whether the program ever finishes or not. So the question is, can we write a Ruby program that can make this decision in general, that you can feed in the source of another Ruby program and the input it's going to read and decide whether that program loops forever? And this question is called the halting problem, right? So I want to look at a couple of examples to try and develop an intuition about how difficult this problem is. Like, is this super easy or is it quite hard? Like, what are we looking at here? Here's another program. So this program reads in a string from standard input, and then it just replaces all the characters in the string with an asterisk and then prints it out. And by looking at that for 10 seconds, you can probably convince yourself that that program is going to finish for any input that you feed into it, right? But the reason why that program always finishes for any input is quite subtle and is dependent on quite a sophisticated knowledge of the semantics of Ruby. This program always finishes because standard input is an I/O object, and when you send the read message to an I/O object, you get a string object back, and when you send the length message to a string object, you get a non-negative integer back. And then if you keep sending the minus message to a non-negative integer with 1 as the argument, you'll get another non-negative integer back. And if you do that enough times, you're guaranteed to eventually get a non-negative integer, which when you send the 0 message to it, you're going to get true back. And so that loop's going to finish and you're going to print out the output. So for you to write a Ruby program that can understand all of that stuff I just said and figure out that that program is guaranteed to finish for any input seems like it would be quite complicated. I mean, there'd be a lot of engineering involved. That doesn't mean it can't be done. It just means it would be hard work. So those first two examples I showed you were quite trivial. This one is significantly less trivial. Let's look at another example. So this is a program that initializes a number, n equals 4, and then it checks to see whether n is the sum of two prime numbers. And then assuming that n is the sum of two prime numbers, it increments it by 2 and keeps looping. So this is going to check successively larger even numbers to see whether they're the sum of two primes or not. And if it ever finds an even number that isn't the sum of two primes, it will print it out and tell you what it is. So does this program finish, or does this program never finish? And the answer is we don't know. Right? This program is checking the Goldbach conjecture, which is like one of the oldest and most famous unsolved problems in number theory. This dates from, well, not the program, but the conjecture dates from 1742. And we don't have a mathematical proof that that every even number is the sum of two primes. Now, we've checked all of them with a computer for even numbers between 4 and 4 quintillion, and they all are the sum of two prime numbers. So it seems empirically quite likely that all even numbers are the sum of two primes, but we don't have a proof that there isn't some astronomically large even number that isn't the sum of two prime numbers, right? So this is even harder because we've been working on this problem for 250 years. If you could knock out a Ruby program that could read this in and tell me whether it would finish or not, then I'd be pretty impressed, right? Now, what that suggests to us is that this is not only hard, it kind of seems like it would be too good to be true. If you could write that program, it'd be almost unbelievable that you could do it. But even that doesn't constitute a proof that it's not possible. It just means that, sometimes amazing things do happen in science, right? So let's just say that it was possible to write this. That would mean that we could write some kind of method in Ruby like this. This is very like evaluate. But instead of actually running the program, it parses it, and then it just kind of walks over it and analyzes it and makes some decisions about the program, and then it tells you whether that program will halt on the input you've given it or not, right? And in particular, this can't work by just executing the program, because we want this halts method to always come back and say true or false, right? Whereas if it tries to evaluate the program, then if the program is one that loops forever, this halts thing's never going to come back with an answer. It has to be more sophisticated than that. So if we had this, we could ask it questions like, does this program halt when you give it this input? And it could say, yes, it does, because all that program does is just print out its input. Does this program halt when you give it this input? No, it doesn't. That program just sits in an infinite loop. So if it was possible for us to write that, then we could write this method, which is like that evaluate on itself, right? We just give it a program, and it tells you whether when that program runs with itself as input, whether that program ever finishes or not. And if we could do that, then we could write this longer program, which reads in a program from standard input, and then checks to see whether that program loops forever or not, and when it's given to itself as input. And if that program does finish when it's given itself as input, then this program here loops forever. It does the opposite. Whereas if that program loops forever when it's fed to itself as input, this one immediately finishes. So this program I'm going to call doTheOpposite.rb. And as before, I'm going to ask the question of, well, what happens if you feed this program into itself? So this program doesn't print anything out. This is just a program that we're going to feed it into itself as input. And so there are only two things that it can do, really. Either it could eventually finish, or it could loop forever. But for a very similar reason to the does it say no situation, neither of these is actually acceptable. If when you feed this program to itself, it eventually finishes, then that means the answer, that means like it should have done the opposite. So if this program finishes, then it should have kept looping forever to indicate that it was doing the opposite of what it actually does. And likewise, if this actually loops forever when you run it, then it should have done the opposite of that and eventually finished. So neither of those is acceptable. So this is a problem, right? Every real Ruby program that you write has got to either loop forever or not loop forever. And whichever of those things happens, in this case, that halts method that we wrote is going to have made the wrong decision about it. We've kind of caught it in a trap by building a special program that causes it to always be wrong. Whatever answer that halts method gives turns out to be wrong. And, so this do the opposite.rb is like with the does it say no program, we've managed to construct something that forces it to give the wrong answer. So here's how the argument goes. If you could write that halts method in Ruby, then you could use it to construct this special program that forces that halts method you've just written to be wrong about at least one program. But of course, for that halts method to be correct, it would need to be right about every program, so it must be impossible to write that method and have it always give the right answer. So that's cool, but who cares? Oh, some sympathetic clapping, thank you. We never actually want to ask a computer whether a program is going to loop forever, right? But we do often want to ask computers other questions about programs. Like, for example, we like writing tests. And tests are us teaching our computer to answer questions about programs for us. So, if my boss comes to me and tells me that my task this month is to write hello world in Ruby, then because I'm a responsible software craftsman, I'm not just going to sit down and implement hello world. I'm going to write a test first, and then when I've got the test, I'm going to go and then write the implementation. So ultimately, what I would like to do is to write some kind of method like this that can take in a program and some input, and then parse and analyze that program and tell me whether that program prints hello world or not, and just return yes or no. So I'd like to be able to say, does this program print hello world? This program that reverses its input, if I give it that string, does it print hello world? And it should be able to say, yes, it does. That's true. Whereas if I say, does this program, so a different program with the same input, this is the thing that just upcases its input, does that print hello world? No, it doesn't. And that seems kind of fundamentally reasonable. It seems like the kind of thing that we should be able to do. But unfortunately, if it was possible to write this program in Ruby, then you could also write this, which is an implementation of halts that uses the prints hello world checker to give the right answer for the halting problem. So it does that by building a larger program which contains the program you've given it, and all it does is just evaluate that program, and then after it's evaluated that program, it prints out hello world. So if the program you give it finishes, then this larger program prints hello world, and if the program you give it never finishes, then this larger program does not print hello world. So we've connected the two problems together. And obviously the problem here then is that if we could write that prints hello world method in Ruby, then we could use it to construct a correct implementation of halts that was always right. But it's impossible to correctly implement that method in Ruby, so it must be impossible to write that prints hello world as well. So the conclusion here, I'm sorry to tell you this, that not only can we not ask, does this program halt, we also can't even ask, does this program do what I want it to do? And that includes, checking that a program meets its specification and that a program doesn't contain any bugs. This is a problem that Apple have. They'd like to be able to automatically check whether a submission to the App Store calls any private APIs or has crashes in it or whatever. And it's just not possible to do that in general. And this claim is called Rice's theorem, right? And a way of expressing Rice's theorem is to say that any interesting property of program behavior is undecidable. And just to define some terms there, interesting means that any given program may or may not have that property, so it's interesting enough that you want to check for it. Behavior means what the program does when you run it, like the function it computes. So that doesn't include properties like, does the source code of this program syntactically contain the literal string hello, because you can just look at the source code to see that, but it's if you're asking questions about what happens when you run the program. And undecidable just means that you can't write a computer program to decide this question in general. And so, this is a massive downer. This really sucks because it means that all kinds of things we would like to be able to ask computers about programs, they're just not able to always give us the correct answer. So I was quite upset when I learned this. And I wanted to find out, why does this happen? And when you look into it, it turns out that, fundamentally the problem here is that you can't look into the future and predict what a program's going to do, right? The only way to find out for sure what a program is going to do is to actually run it. But when you run a program, you don't know how long you have to wait for it to finish to see what it did. And some programs are going to have this property that they loop forever. And so when you're waiting for a program to finish, there's no way of knowing whether it's going to be one of these programs that never finishes, or maybe it's a program that's about to finish if you just waited a little bit longer. And the underlying issue here is that any system that's got enough power to be self-referential, which universal systems and programming languages are, because programming languages manipulate data and programs are data, so they can refer to their own representations, it can't correctly answer every question about itself. And for the mathematicians in the audience, this is the essential content of Gödel's first incompleteness theorem, right? If you've got this situation, then you need to step outside the self-referential system and use a different, more powerful system to answer questions about the original system. And that's what I was saying about RUB. We would have to step out of the RUB language and use a more powerful language to write an interpreter for it. But this time, unfortunately, there is no more powerful system for us to upgrade to, right? These universal systems, the most computationally powerful things that we know how to make, there is essentially nothing better than a Turing machine or the Ruby language. So just to wrap up, this is very depressing. How can we cope? Like, how do we live in this world? Like, why don't we all just, should we all just, leave now and all go home and have a cry? Does this invalidate our entire profession? And I hope that the answer is no. And the reason why is that we've got some coping strategies that allow us to handle this awful situation, this terrible universe that we find ourselves living in, right? I'll give you a few coping strategies, and hopefully that'll make you feel more happy. So firstly, we can ask these undecidable questions, but we can just give up if the answer to those questions can't be found in a reasonable time. So if you wanted to know whether a Ruby program prints hello world or not, you could just run it for 10 seconds. And if after 10 seconds it hasn't finished and printed out hello world, you could just Control-C it and say, I give up. Like, it didn't do what I wanted it to do within a certain amount of time, and so I'm not interested anymore. Now, of course, if you do that, there's a risk that that program would have actually printed hello world after 11 seconds, and you should have kept waiting. But if after 11 seconds it hasn't printed it, then maybe you should wait another second, right? So if you use this strategy, sometimes you're going to be wrong, but maybe that's okay. Another thing you can do is, instead of asking a very large, undecidable question, you could ask several small questions whose answers provide evidence for the larger question that you're actually interested in. An example of this is that instead of trying to prove that a program meets its specification, you could just write a bunch of acceptance tests for that program. And you could say, I've got some examples of inputs to this program. I've got examples of what the output should be like. I can evaluate it for each of those inputs and check that the outputs match up. And that gives you a degree of confidence that your program is generally correct. It doesn't tell you for sure that your program is generally correct, because you might have inputs that you haven't tested for that actually make the program go wrong. But if you do enough of these, then you can develop some confidence that it's doing the right thing. Another option is to ask decidable questions by being conservative. And an example of this is in optimizing compilers, they do an optimization called unreachable code elimination. Unreachable code is code in your program that's never going to be run. So if you say if false and then have a block of code, the compiler will try to remove that code for you. Now, unfortunately, reachability is an undecidable property because of Rice's theorem, but what compilers do is they try to underestimate how much of your code is unreachable by just looking for particular patterns. They know that if you put if false and then a block of code, or if you put return halfway through a method, they can spot that there's some unreachable code there. So they can remove some of the unreachable code, but not all of it. There may be some code lurking that the compiler doesn't have a pattern that allows it to spot that that code's unreachable. And a final coping strategy here is you can take your original program and turn it into an approximate version of that program, a simpler version, and ask questions about the simplification. And this is a way of thinking about how type systems work. If you've got a program that is about, static type systems, I should say, if you've got a program about values that's like x equals 1, y equals x plus 2, you could turn that into a vaguer program about types that says x equals some integer, y equals x plus some integer, and then ask questions about that abstract version of the program, which hopefully that type system is not going to be universal, so you can make decisions about it, and then that gives you information about your original program. So you can't have type systems that can guarantee that programs are free of all bugs, but you can make type systems that can guarantee the absence of certain kinds of bug. So that's all I wanted to say, really. If you are interested in this kind of thing, as Josh mentioned, I've written a whole book about this kind of thing, using Ruby to explain Turing machines and the halting problem and type systems and interpreters and compilers and stuff. So if you're interested in that, there's a website for that book. O'Reilly have given me a discount code if you want to have some money off of it. That's the end. Thanks very much.